So today I'm going to be making some Wakefield simulations. First, the longitudinal Wakefield simulations and then the transverse Wakefield simulations. But then before we get into that, let's just see a rough overview of what Wakefields are. Now we are still dealing with accelerating cavities or accelerator cavities, whichever. Okay. And yeah, it so happens, and the whole concept of accelerating cavities is to accelerate particles. But then something happens when you move a charged particle or a beam through such structures. As you can see, I hope my mouse movement is visible, going in circles around the cavity. Okay, so it so happens that when you have charged particles or beams of particles moving through an accelerating structure, because of the nature, because of the shape of the structure, so you have kind of an expansion of the area and then a contraction also. I'm not going to go into so much details, but then because of this profile of the cavity, you have that when the beam or charged particle moves from this end of the accelerator into this other end of the accelerator after passing through this enlarged space, you have that some electromagnetic energy is left behind in the cavity, and this is what excites higher order modes. Now, your Wakefield simulation solves the Wakefield equations, of course, and the Wakefield equations are derived from moving a test charge just close to the original charge and then observing the effects of the field that is deposited by your main charge, if I would call it that, and then I'd call your Q2 the test charge. So these the CST, I think this should be for CST. Yeah, the CST application, maybe help page or documentation page for Wakefield solvers. So, okay, where was I? Yeah, so your wake equations are basically derived from trying to quantify the effects of these deposited electromagnetic fields, electromagnetic energy on a test charge moving at a particular distance s from the main charge traversing the cavity. So this is the momentum equation. So this describes the momentum from the Lorentz force, the momentum of the change in momentum of particle Q2 based on the deposited fields, which is your E and your B fields. And then from there, you could derive the wake potential or define the wake potential as this function that is here. So for this, we have the longitudinal wake potential defined as this, and no, that's the general equation for the wake potential. Then your longitudinal wake potential, which is doubly parallel, is defined as this, or is it wake function? I think it's, yeah, wake potential function, something like that. So this is your longitudinal wake potential function, and then this is the transverse um, wake function defined as this. And this equation is solved in the time domain by the CST Studio Wakefield solver. And what you're actually interested in is not the time domain response of the system, as the system consisting of your cavity and your two beams, but what we are kind of interested in is the Wakefield impedance. Yes, and your Wakefield impedance is just the Fourier transform of your wake function, your wake potential function. So your longitudinal wake impedance is the Fourier transform. So we are transforming from time domain to frequency domain, and then you have your transverse wake function also transversing, moving from your time domain to your frequency domain. So that's the um, transverse wake impedance function. Yes, got that. So, and then what you could evaluate from the wake impedance simulations is your loss factor and also your kick factors, which are kind of indications of the higher order mode power and higher order mode effects in the accelerating cavity. So this was just kind of a rough introduction. You could read through the page and also maybe check out some materials on Wake Wakefield solvers. So now we um, head into CST Studio and start modeling. Um, okay, so want to go to 3D simulation and click on that. We are going to particle, and yes, we are welcomed, maybe so to say, with the home page and not the home page, but then the file. Yeah, I'll just call it file page. So we have untitled, and we have the home. Yeah, it's the home tab, and we have some settings here. But what we're interested in is the setup solver. So if we should click on setup solver, we see the eigen mode solver and all your different other solvers. But what we're interested in is the Wakefield solver. So we click on that. At this point, we could also save. We could also save the project. So I would maybe save the project somewhere here. So what I'll be running the Wakefield impedance simulation for is the Tesla cavity. So I would call this the Tesla or Wakefield longitudinal wake. Oh, come on, longitudinal, if I can spell that correctly. Wake Tesla cavity. So I'll save that, and then I would have to move this a bit and change the unit. So I like working in megahertz. I know you could also change it to gigahertz, and but definitely change it to millimeters, or else you have like really big cavities. So okay, that's done, and I could save again. Now, first of all, we need the cavity model. Of course, we need the cavity model, and I could either model I could either import an existing model from a sub project, so maybe from some analysis or some model I did before, or I could build my own model just like it's shown in the other video. That's modeling and accelerating cavity. I think you should be on the channel somewhere. You should be able to find it, or if I can, I would link it up in the description. So you could just go and create the superconducting cavity. But then I don't want to waste so much time since we're focusing on wake impedance. So I'll just import from a project. So I have here Tesla cavity, and I'm going to import this geometry. So voila, I have the geometry imported. Now this is the original Tesla cavity. I think I also mentioned in the other video it's a 9 cell cavity, but this is a 5 cell cavity scaled to operate at a fundamental mode of 801.58 megahertz. If these things don't make sense to you, it's no problem. I just want to let you know that this is not the exact Tesla geometry, but a scaled version of it. So I like to turn off, it's very painful, the working plane. And I just go to view and then I can turn it on or turn it off. So I like to turn it off. So now I have the model. Now what should I do? Now I have the model, and if you remember, um, yeah, we need the model, and also we need some sort of source, electromagnetic field source, which in this case is your particle or your beam. In this case, is actually the beam, a collection of particles. So I could just go ahead and define my boundary conditions. So let's do that first. Um, or first, let's create the source. So I go to particle beam, and when I click on the particle beam, I have some settings. So I leave it as particle beam 1, and then the shape is Gaussian. I mean, only Gaussian is available. And then the charge, I'll just leave it at 1 e raised to power minus 9 coulomb. And then the sigma, okay, now for the definition of the sigma, it depends on the frequency range that you're interested in. So for this cavity, it's fundamental mode frequency is 801 megahertz. So I might be interested up to maybe 4 gigahertz or 3 gigahertz or so. So this I mean, you can look at the link here. Maybe I could just show you the presentation also, and hopefully I can navigate back to this page. So it's higher order modes by Frank Malhauser. I think it was a lecture given, yes, hands-on course by this. So you could check out this presentation and read also through it to gain more knowledge about higher order modes excitation in cavities. So okay, now I have to look for this. Okay, yeah, I got it. So depending on the um frequency range you're interested in, for me I'm interested in 0 to about 3 gigahertz. So that will determine my bunch length. And you see for 50 millimeters you have up to maybe about 3 gigahertz, and then it's cut off. And for 25 millimeters you have up to 6 gigahertz, and then for 10 millimeters it keeps increasing, and then you see every other thing here. So just as an example of what you get, I think I saw an image here. Okay, so basically this is an example of what we get. So this is your wake potential, which is in time domain, and then this is Fourier transform FT, Fourier transformed, and then you have your wake impedance, which is your frequency domain. Now you have the accelerating mode, and then the peaks usually um, represent resonant higher order modes, as you can see here. And then when it's not so, when the peak is not so sharp, it represents traveling mode, so modes that travel inside the beam pipes. So the frequency range, so we have such kind of plot when we run our Wakefield simulations up to whatsoever cutoff frequency is defined by the sigma, which is the bunch length. So back to this. For this, I'm interested in 0 to, I mean, about 3 4 gigahertz. So I'm going to use 50 millimeters as the bunch length. So sigma 50 millimeters. And then for this, um, transmission line is more accurate than analytical, and you could also see the reason why on their page. I don't know, I think if you search through their help page, that's CST Studio's help page, you would see the description of because it's different methods that is used, the current injection scheme. And from my own kind of little study, I saw that transmission line was more accurate. That's comparing with analytical results for a simple case. And then the beam direction is in the Z. Now, whenever you model your cavity, always try as much as possible to make um, the cavity looking this way, such that the beam would move in along the Z direction. But of course, if you do not have yours in the Z direction, you could always change it to plus X minus X. So this is plus Z, so it goes from right rather to left. I mean, depending on how you look at it. So some other settings that we have to do is now the Wakefield calculation. Now the wake integration method direct is not so accurate. I think the most accurate is indirect test beams. Is it? Yes. If I remember correctly, it's indirect test beam. So we're not going to bother about the other ones for longitudinal Wakefield impedance calculation. We are not going to bother about this, but then for the transverse, we are going to bother about this. So basically, this is the integration path shift. So basically, this just defines along what path your integration should be. Currently, for the longitudinal, we are just interested in the mid-axis, so 0 comma x comma y is equal to 0 comma 0. But then for the transverse, we would shift the beam, we would offset the beam a bit to in the x direction and also in the y direction. But I'm getting ahead of myself, so for now, just leave this as it is. So yes, and lines per sigma you could define it, but for the simulations I've done, I've found that 10 is usually enough. And one other thing you could do is you could preview the beam. So this is the Gaussian beam, and then this is the definition of the Gaussian beam. And yeah, I think that's it. Hopefully I didn't miss anything. So we've defined cavity geometry. We've also defined particle beam. Now the boundary conditions. So we, okay, of course, define the frequency. So the maximum frequency, I could leave it at 4,000, or should I simulate shorter? Okay, maybe I'll leave it at 3,000. The maximum is, I think, maybe 4,000, 5,000 for a 50 millimeter bunch, but I could also truncate it with 3,000 to 3,000. Then, okay, megahertz. If you're working in gigahertz, that would be 3 gigahertz. And then the background, yeah, the background, of course, is perfect electric conductor. And the boundaries. So the boundary conditions, you could have electric for this, but then the Z min and the Z max, it's your open boundary conditions. Hopefully there are no symmetry planes. Yes, no symmetry planes. I mean, for the longitudinal Wakefield, you could define um no symmetry plane, because if you define your symmetry plane, then you have just some modes. You don't have all the modes. You have just the modes that correspond to that. You have just the modes that correspond to that symmetry plane, so that have their fields symmetric about those planes that you define. So just leave it no symmetry planes defined. And yes, I think that should be it. Now another thing that could be done is um waveguide ports could be added to this end. So you could have a waveguide port boundary condition that could be added to this end, but then we are not going to look at that currently. So yes, I think with that we are set to run our simulation. um let's see, hopefully I'm not missing anything. And then now for the setup, simulated wake length. Now your simulated wake length, I don't know if there's a description here how to describe it. So your simulated wake length kind of defines, I would say roughly the amount of time you for the amount of time you kind of observe the oscillations of the field deposited in the cavity. So the more the wake length, which is the more the time, the more resolved the Wakefield impedance plot would be. So if you use a very short wake length, you would have a not very resolved you would have not very resolved peaks. So you'd have some kind of blobby shape, and then yeah, I mean basically you don't have these peaks. The more you refine the longer your wake length, the more refined these peaks are. I don't know if there's, okay, I can't really find any. Okay, here you could also see the spectrum. So the spectrum, this should be a bunch length of this should be a really short bunch length, because you see spectrum is getting up to 19 gigahertz. So I don't think I can find any of the images, but then yeah, basically short wake length, short simulated wake length, you do not have these resolutions in the peak, so you can't really identify the accelerating modes or the resonant modes. But wake fields imply longer wake fields imply yeah, more resolution. But then, okay, this is getting into too much theory. Let's just run the simulation. So for my purposes, I see that a hundred a 100 meter, so that's 100,000 millimeters wake length, is usually sufficient for all the purposes I need it for. I mean, for me, it's just to identify the modes. But for this, I'm going to use, I don't know, so that it doesn't take much time. If it takes much time, maybe I'll just cut it out. I'm going to use 25,000. Yeah, let's see how that. So that's 25 meters. Let's see how that works. So I'm not going to turn on more adaptive mesh refinement. Okay, hopefully I didn't miss anything, and we click on start. And this would run the Wakefield simulation. Longitudinal longitudinal Wakefield. It would calculate the longitudinal impedances. So just wait for that. If it takes too much time, I would cut this section off. So the Wakefield simulation is done. I had to pause that. I think it took about maybe 2 or 3 minutes before it successfully run. If you have longer wake lengths, then you have to wait for not forever, but for very long times. So now that it's done, we can view our results. So we go to 1D results and then particle beams. If you can see it here, particle beams, and go to particle beam one, because of course we have just one particle beam. And then you look at wake potential, and then you have these crazy spikes. So yeah, so this is the simulated wake length, which is in millimeters. So that's 25,000 millimeters, which is 25 meters. So then you have your y, and then you also have your x, but then we are just interested in the z. So this is what we have, which is your wake potential, which is the solution to to these um to these equations. No, that's this one. So to these equations, so you have your longitudinal and then your transverse. Your transverse is your x and y. But then we are not interested in that for this simulation. We just need w parallel. So that's what you have here. And then for the wake impedance, because I mean this doesn't give us any information at all. But then what we're interested in is in the wake impedance. So for the wake impedance, this is what we have. So this is the longitudinal wake impedance, that's in the z direction. You could also have the transverse. I mean it's not very important. It's like very small, and also this is very small. So this is what we have as the longitudinal impedance. It cuts at 2200. Why is that coming? Let me see. Okay, this is supposed to get to, so 50 millimeters. It's supposed to at least get to. Hmm. Okay, I think maybe it truncated at somewhere here. So I think it truncated at somewhere here. So that's okay. I'm not going to run it again. I thought it would get up to 3 gigahertz or maybe 4 gigahertz, but it truncated at 2 point something gigahertz. If we used 25, then I think we could get up to maybe 4 gigahertz. So now that's it. We could view it in linear, or I think we could decibel magnitude. No. I think it's linear. Yeah, and then log. Yeah, of course we have it as logged. Okay, had to pause a bit there to check because now if you notice on this, so log. Now if you notice on this the impedance, you see all these artifacts, which is kind of noise. So I knew I missed something in the simulation, and let's go back and fix it. So if you have such noise in the signal, you would have to check your particle beams, and then you go to your Wakefields. And what I forgot to include is apply cosine square filtering, which kind of helps to reduce, or I think most of the time, I think for me it removes the noise, I guess, totally, as you would see. So you apply the cosine square filtering, and then okay, yeah, delete current results, and yes, just run your simulation again. So you see 25,000, no other thing has changed, and then you run your simulation. So I'm going to pause again and come back when it's done. So the simulation is done, and yes, now we can go back, particle beams, wake potential, and then wake impedance. Now you see a better looking Wakefield impedance plot. So if you should do this, then you have up to 2000. Okay, I don't think I'm satisfied with this because I want to show the other modes. Actually, this is, my bad. This is actually a Tesla cavity, because now what you can see here is that so if I should go to if I right click, so if I right click on the plot and go to move axis to maximum, then I see that the resonant frequency, which is your first mode, which you're seeing here, is at 1300 megahertz. So yeah, that was my bad. I thought I scaled the cavity, but this is the original Tesla cavity geometry dimensions, but then with 5 cells. So when you could see clearly that the resonant, the fundamental mode is at 8300 megahertz. So what I can do is reduce my, I mean, I just want to show the higher order modes, and you see some other mode peaks. Hopefully they show very well. Now if you look at this, it's also not very sharp. I mean, if you should take longer wavelength, then you see that it's very sharp. Then you still have maybe some noise, smoothing, but then it's better than when you didn't have cosine square filtering on. You could read about the cosine square. I think it's it root cosine or cosine square. I think it's root cosine, but then you could read about it on Wikipedia. So what I'm going to do now is I'm going to run the simulation for, maybe I'll use a longer wavelength, and also change my bunch length to 25 millimeters. So let's see, I'll change it, run it, and then pause the video. So I'm changing this to 25 millimeters, and okay, 25, not 23. And okay, then I also want to, I mean, looking at this, I would hope that it would give me maybe up to 4 gigahertz. So I also want to change my high order mode, my frequency range to 4000. And okay, and what next? So I've changed my bunch length, and I've changed the frequency. So yes, so 24. Okay, let me change it to 50,000, not 500,000. 50,000 millimeters. That's 50 meters. So I'll start, pause, and then come back when it's done. Okay, and this simulation is done, and yes, so I don't know how long that took, but I don't think it was still very long. So we go again to, I mean, we for the wake potential, we see it's up to 50,000 now, and when we get to the wake impedance, you see it's okay, log. You see it's a bit more refined, a bit sharper, the impedance peak, because we increase the wake length. So now, reducing the bunch length, we see that the simulation was up to about, let's see, move to maximum, and then I could move it here to about 4092.5 or 4092 and 90 gigahertz. So we can also move to the maximum to see the fundamental mode. So that's at 8300, but okay, you have some maybe numerical error, so it's 8298. And then you see the higher order mode. So this is your fundamental mode, and then basically everything that comes after that is your higher order mode. So for my own case, what I mostly use the Wakefield simulation to do is to, in some cases, calculate the impedance, although it's not because we, okay, that's technical. But yeah, that's it. I just use it to check out the areas where not only, but check out the areas where we have the higher. So these peak modes basically are the potentially potentially dangerous modes. So we have, I think, one. If I could zoom in, then you have still not very resolved, and one, and then two, and then when you keep increasing it, you basically have a lot of the other ones. But in my experience, the ones that are usually parasitic, the one we usually are concerned about is the first and the second, at least for the longitudinal higher order modes. For the transverse higher order modes, we are concerned with a different set. So that's it for the longitudinal higher order, um, longitudinal Wakefield simulation. And then we could, of course, do some post processing, result templates. We could um, play around with the results as much as we want, but then I'm going to keep this video, yeah, at 30 minutes exactly. So in okay, it's going to be a bit above, but in some other simulations, maybe I'll show how to go about calculating the loss factor from your Wakefield impedance simulation. And but then before that, I'll do a video on transverse Wakefield impedance simulation.